Next up, we have Harwayne Gidansky. He's with BNY Mellon. Jared has over a decade of engineering experience spanning numerous industries, which include finance, biomedical engineering, defense, robotics, textiles, manufacturing, software development. Sounds like he's done just about everything. Jared is currently a VP at BNY Mellon, where he serves as Deputy Global Head and North American Lead of Emerging Business and Technology Group. Jared received his degree in electrical engineering from Cooper Union and his PhD in electrical engineering from Yale. Please join me in welcoming Jared. Thank you.
Hello all. Sorry about the technical difficulties. Can people hear me this time? I heard that I was not loud enough last time. I actually think I'm better without the microphone. I feel like I get too quiet with a microphone. Oh, so I have to use the microphone? So oppressive. As was stated, my name is Harwayne Gidansky. It's a lot of letters. I go by HG, so jaredhg.com, right? When you're a kid in kindergarten, you don't want to write out 17 characters. Today I'm going to talk to you about blockchain for security and resiliency. So let's get going. All right, so security and resiliency, this has become a really big thing in the finance industry. You hear it a lot. What are the triggers for this? Well, one is that we do actually care about being stewards of the global economy, and we care about making sure our customers have access to reliable and secure systems. But there have been a number of other external triggers that have pushed this forward as well. There's a presidential policy directive around critical infrastructure, which most financial infrastructure is, or much of it is. The Department of Homeland Security, Department of the Treasury have created specific guidance for the financial sector. And then there's industry standards that have risen, such as the sheltered harbor provisions, which we'll talk about a little bit towards the end of this. Now that we've said, well, all right, great, you have these triggers for these things called security and resiliency, what do those things even mean? Security is, you're talking about proactive means of protecting infrastructure. So physical means, cyber defensive means. Resiliency is an ability to prepare for and adapt to changing circumstances and threats, as well as ability to recover from an attack or an outage of some sort. Now, security and resiliency was like a pretty vague, kind of high-level overview. Specifically, you have to look at what it is you're trying to secure against and be resilient from. This is the Threat Taxonomy. This is from NIST. So they have 4 broad categories: adversarial, malicious actors, people trying to attack you or exploit you, sabotage you for some reason, self-sabotage, obviously. Accidental, so fat finger stuff, right? Tripping over the cord or something like that, or cat walks over the keyboard. If you watch The Simpsons, you have that, the little bird thing that keeps on hitting yes by accident and causes a meltdown. It's a really obscure Simpsons reference. Anyone? Yeah. Thank you. That's old episode. Structural failures, so your servers, crap out on you. Your UPSs fail. Environmental, these are your attacks, hurricanes, floods, all the kind of biblical stuff. Very exciting, right? So when you kind of look at those threats, and we have to be kind of resilient to all of them, you break down across those areas security and resilience. So security goals, accountability, so you want to be able to know who's doing what and hold them to account for it. Auditability, you want to be able to keep track of what's going on in the system, both in terms of what users are doing, but also what's going on automatically. Authenticity, again, make sure only the right people are doing the right things, so you don't want Joe Schmo to come off the street and be able to access your core infrastructure. Availability, the system has to have a high level of availability. Confidentiality, making sure people have access controls. Integrity, so knowing that what you see is correct. Non-repudiation, this is the, I didn't place that order type of stuff, right? And privacy, you want to ideally have people to have control over their own information. So these are goals from a security side. So you're trying to protect your infrastructure and defend it against kind of different vulnerabilities such as these. On the resiliency side, this is really exciting. Don't worry, it gets better. These are principles for engineering resilient systems. I don't know, how many of you folks are engineers? out of curiosity? All right, cool. Any of you people have like public safety or kind of military backgrounds, any sort of that sort of stuff, emergency services? Yeah, great. So a lot of this is going to be kind of very familiar to you from either of those perspectives. For the rest of you folks, hopefully you find this stuff really exciting. Maybe you'll become like a resiliency nerd. They have those, I guess. So absorption, this is the principle that if there's an outage, your system should be able to absorb the outage without going down. Physical redundancy, if there are multiple legs of a system, right, outage of one doesn't cause the failure of the other, so you want your systems to be kind of independent and parallel as much as possible. Functional redundancy, let me just check my notes here. Cribbing here. All right, so basically there should be multiple ways of doing things. So for instance, for those of you guys in enterprise IT, if you've ever run a system, production system where you have different operating systems for the same application or to prevent exploits in, let's say, Linux being used to shut down the system, there's also a parallel system that's running in Windows, or vice versa. Layered defense is the idea that critical decisions should be done by multiple people. This is the two people turning the keys to launch the missile type of thing. Humans in the loop. For you crypto anarchists, I'm sure you're going to disagree with this one. There's definitely some discussion here. But it's the idea that you should have a human making decisions that require cognition. The idea behind this, and maybe this is the better principle rather than focusing on the human element, is to prevent sort of cascading failures, right? Where because you have some automatic setup, you have a series of automated actions that don't account for some tail condition, and it causes some sort of catastrophic outage. I'm gonna refer to the blackout on the East Coast in 2003 a bunch, right? Branch hits a wire in Ohio, I think, and it shut down the entire eastern seaboard. So, that was a cascade failure, right? And it violated a bunch of principles that we're going to be talking about. Reduced complexity, always a good sign, right? The less stuff that's in there, the less stuff that will break. So you want to have as simple of a system as possible that creates the output that you need. Reorganization, this is the idea that your organization structurally or technologically should be able to adapt to changing circumstances. This thing is going to kill me. Changing circumstances or threats, right? Think Maginot Line, another, right? Oh yeah, the Germans just came across here. We'll just build these big fixed fortifications, but the French forgot that airplanes existed, right? So it didn't work out very well with them. So you want to make sure that you're able to adapt to circumstances. Repairability, this is the idea that if you have an outage, either total or partial, that you have some ability to ramp your systems and operations back up again, preferably relatively easily and in some sort of known timescale. Localized capacity is the idea of locality, right? So one server goes down, the whole data center doesn't go down. They'll have access to their data locally and be able to continue processing on it. Loose coupling, this is going straight back to our power outage example. You want your systems to be somewhat independent of each other, so that way a failure in one part doesn't cascade all the way through and create some sort of large outage. Drift correction is the idea of as you move closer towards the edge of some sort of your resiliency boundary, as you get closer to some sort of an incident, you have the abilities to either basically modify your operations to prevent the incident or modify them to mitigate the severity of the incident. Neutral state is the idea of essentially there has to be some good governance. Those of you who know me from EEA know how big I am on governance. And kind of being as, taking as much time as you can to make decisions. So also, good governance structure, taking your time to make sound decisions. If there's no urgency, take your time, gather more information. Internode interaction, again, this is just peer-to-peer interactions. You want to make sure that you have as much connectivity within the network as possible, so that way there are no single points of failure. And of course, reduction of hidden interactions, having greater transparency and understanding the system allows you to prevent people from exploiting it, or that's kind of from a malicious action standpoint, maybe a security standpoint, or for there to be some unintended failure mode that you don't see because it's kind of obfuscated. Now, this is from the World Economic Forum. I work for a bank, so forgive the slight finance heavy-handedness of this. These are the key value drivers for blockchain that the World Economic Forum put out. So think about this, and then think about the context of the security requirements and the resiliency requirements we just went over. Operational simplification of things. Efficiency improvements. Risk reduction. Time reduction for uncertainty, so that's clearing and settlement time reduction. Liquidity and capital improvement, you can make some like macro arguments on that, not a direct mapping. Fraud minimization, audit assurance, efficiency, and then cybersecurity and resiliency. You'll notice that a lot of those attributes greatly overlap with several of the factors we talked about, both on the security and the resiliency side. What this seems to indicate is that from a security and resiliency perspective, there's a huge role for distributed ledgers, blockchains, this sort of technology to serve. And in fact, it may even become a requirement as regulators wrap their hands around this more and more. Not only, by the way, in the finance industry, but in all critical infrastructure. This is kind of a very toy example, right? This is the world as it exists today, right? You have your clearinghouse. If there's a problem, none of the four parties can operate. In the distributed ledger world, do I have a mouse cursor that moves? It doesn't. All right, fine. We'll work with it. So in the distributed ledger world over here, one of the nodes goes down, no big deal. The other three nodes can keep on operating. Notice that this kind of incorporates several of the resiliency principles we just discussed. Ideally, your systems will be fully parallel systems, and distributed systems such as the ones that we talked about today, and you've heard a lot about different technology stacks, are inherently resilient. The probability of the system being operational is 1 minus the probability of node A is up times 1 minus the probability that node B is up, so on and so forth. What happens with this is if you have 6 nodes with 90% uptime, which anyone in IT knows 90% uptime is a joke, you can get 6 nines of reliability, which is pretty hard to get out of monolithic systems, but way easier with distributed systems. And if you want some more reliability, put a 7th node in there. So, this is kind of interesting. Right? This is like pretty exciting. You can have a relatively easy to build, low maintenance system, 90% uptime, which in parallel through distributed networks, through a distributed system, gives you 6 nines of reliability. So this is pretty cool. All right, so enough of the background information. Let's talk about some things that we're doing today to solve actual problems. First thing I'm going to talk about is something called BDS 360. This is in production right now. BNY had a problem. The Fed had declared large portions of our infrastructure as critical infrastructure. Outages there would have a global impact. We weren't particularly happy with the current situation. We said we want to make sure that we are offering the best services to our customers and that we're doing the best job possible as one of the stewards of the global economy. What would happen was we only had end-of-day snapshots for this system. All right, so we had the previous day's snapshots. We would go through an entire day. At the end of the day, you do the final reconciliations, and if there were any errors, you'd have to go start tracking back through the day to figure out where there was an outage, where there was a mistake, all right? Usually you'd have to call a bunch of clients, they were unhappy. You'd have to call the Fed, you get window extensions, they were unhappy. Everyone was kind of unhappy, all right? Because of the way the system was architected, you really could only detect these problems at the end of the day when everything was all said and done. We didn't think this was acceptable, and we're always striving to be better than the bar set through regulation. And so we said, all right, we're going to find a solution to this, and we're going to make a couple of assumptions. One, we're going to create a worst-case scenario. That means we're assuming that there could be malicious actors. What that therefore implies is that it's not sufficient just to know what the correct state is, but you have to prove that it's the correct state. And we put this into requirements. Number one, we need to make sure that we have some solid version of the truth somewhere, all right? So our end-of-day snapshots, for instance. We have to be able to reconcile our production system to some sort of audited system in close to real time, some sort of regularity, so we don't have that end-of-day situation. And we're going to use that to detect issues earlier and then manually recover from them. Pleased to say all 3 of those have been in production for several months now, maybe even close to a year. And the rest of these are kind of in the queue to be implemented. So automated recovery, right? If there's an issue, instead of having manual recovery, at least automating or semi-automating that process. Real-time validation. So you'll hear about this. We use a fork of the Bitcoin blockchain with some modifications to underpin this. So we just kept 10-minute block times. We're looking to drive that down to near real time, second, probably sub-second. You want to have a market viewer where people can go and see what the current status of things are in the event of an outage or some sort of disruption. You want to run analytics on top of this so you can detect unusual activity. And this might actually be in production. It was slated to go into production at the end of Q1 of 2017. And this is the sort of thing of, hey, client X normally does a lot of trading volume at time Y. They're way out of those parameters. Maybe there's an issue. Maybe it's our connection with them. Maybe they're having an outage. Let's pick up the phone. Could be nothing. It could be a Queen's holiday in England, and that's why they're not doing anything. Well, that's a bad example because government securities are US-based, but whatever. And then finally, having a parallel system. This is some sort of cloud system which would have partial functionality in the event of a catastrophic outage. So probably won't have the same throughput and volume, but ability to at least keep things going. So we came up with this thing called BDS 360. We took a blockchain fork, a Bitcoin blockchain fork, removed mining and consensus. We really cared more about the hash chain, the auditability piece of this. What we did is for every security that we have in our system, we created its own chain. We populated wallets of our clients with what their shares are of each security are at the beginning of the day off the previous day's snapshot. And what we got was we have an immutable record. When orders come into our system, they branch out. One goes through our production system. The other order goes through this system. Again, following resiliency principles, right? Two ways of doing the same thing. And what we have is we have now a complete audit trail of all the transactions because of the UTXO model in Bitcoin. We also get all this data transparency, which is good for our analytics and other tools of that nature. This is a screen grab of anonymized data from the system in production. On the top of it, you'll notice there's the blockchain. The thing labeled prod is our traditional production system. The other side, I think it's the right, yeah. The right side of that is the parallel system, BDS 360. If there's an issue, it's discovered, and we start tracking it down. Here's kind of a cool graphic that shows the security is actually moving around in our system. This is our market viewer. The orange dots represent clients of ours, which means we custody their assets so we can see money moving in and out of their accounts. Turquoise represents people who were custodied outside of BNY, which is why we only see stuff moving into those accounts after it moves out of our system. So that's BDS 360. Now, I'm going to talk about something that we're working on now, hope to get in production soon, and it's something called Sheltered Harbor. Sheltered Harbor came out of an industry consortium, which we're a member of, which wants to securely store end-of-day snapshots of account data, account information for financial institutions off-network, totally air-gapped in a way that a catastrophic outage, attack, or natural disaster could wipe everything off the map, and you would lose, at most, 1 business day's worth of information, and probably less. So when you look at the requirements, there are a couple of pieces of this. First is this air gap piece, right? So I have end-of-day account snapshot data. Obviously, everything's encrypted. I send it to someone to store it. Could be tape drives, Amazon Glacier. There are a couple of reference implementations out there. And I'm going to take a hash of what I have on my system and hash of what's on the other side of the air gap, and I'm going to compare those two things. Pretty standard stuff. Any of you folks who kind of deal with communications theory, right, you're always going to check that your hashes match, MD5 if maybe, right, download a file, to make sure that you actually got all the data, the integrities, the data was, integrity was maintained. But there's another requirement, which is that these hashes, once they match, have to be stored in a robust, resilient, and accessible manner. Sounds a lot to us like a blockchain. I don't know. But so we're looking at distributed ledgers as a way of storing these hashes either on some sort of permission ledger between core, key institutions, or maybe some sort of a public blockchain. Although I doubt that's likely going to happen, where you can store all of these hashes, and you'll be able to have complete understanding that one, the data, who owned the data, who's custodying the data, and that the data you've recovered is the data you wanted. All right, that the integrity of the data is complete. So that we hope to have out. We've begun this project now. I don't have clear timelines on it, but hopefully less than a year. I'm trying to pad this year. I don't want to be held to account for this. But that's the Sheltered Harbor Initiative, and that is another kind of resiliency product that we're looking at that relies at least partially on distributed ledger technology. I believe I'm out of time. Sandy is advancing on me. But that is, in fact, my last slide. So here's the BNY logo. And if you have any questions, I know there's a breakout session. Happy to chat with you. Hopefully, I kept you guys awake. I know it's getting a little late in the day. Thank you all very much for your time.